Swayam Prabha. Digital India. Educated India.
So let me continue this discussion on additive manufacturing and geopolymers using binder jetting, specifically large-scale binder jetting. And I just want to illustrate a couple of projects we've been working on. This is a finished project. So in this project, together with colleagues from Greece and Belgium, and Boliden is the company from Sweden that provides the iron silicate slag, the copper slag. We won a European project for developing components that were fire resistant for the building and tunnel use for the protection of structures against fire. And we had several target properties, and these target properties were derived from already commercially available parts or materials. And the density below a certain value, minimum strength, both for flexural and compressive properties. And in order to provide fire protection, the material should withstand temperatures up to 1300 Celsius. And the material needs to be fast setting and at ambient temperature, and the produced component needs to be able to be anchored to an existing structure. So we worked on additive manufacturing together with a company that can make large-scale parts, while the people at KU Leuven developed parts by foaming. So they developed foamed geopolymers for the same application. I already mentioned that we have the copper slag, which is reactive. The reaction rate is slower than metakaolin due to the size of the slag. I mean, we can, of course, grind it, but we don't want to grind below a certain size, otherwise it becomes too expensive. And we added expanded aggregate to reduce the weight of the part. And you see that if you obtain commercially available expanded aggregates, you have some limitations in terms of the maximum temperature at which the material can be exposed. For expanded clay, it's around 1100 Celsius, same for expanded glass. Xenospheres are crystalline or at least partially crystalline materials, so they can withstand a higher temperature. The difference between these lightweight components is that xenospheres are much more expensive. And we used both potassium silicate and sodium silicate solutions. So we used a combination of copper slag, metakaolin, and lightweight aggregate. And we used only industrial commercially available silicate solutions. And you can see that we are able to obtain consolidated parts. You can see here the morphology of different parts containing the various lightweight aggregates. And you can certainly recognize the porous aggregates coming from expanded clay. They are very well embedded inside the geopolymer matrix. We carried out a successful tunnel fire resistant test. And in order to be successful to this test, we needed to follow a certain heating curve, and the board should have not, the temperature measurement on the other side of the board should have not exceeded 180 degrees. And here you can see the experiments that were carried out in a road tunnel in Crete, in Greece. This is the furnace with all the controls for the temperature. This is the part that was 3D printed and attached to the wall of the tunnel. And of course, you could say, well, why are you 3D printing something that is simply a sheet? But there are a lot of areas where you need curved structures. So additive manufacturing actually makes sense. And we tested both foams and 3D printed panels, and the 3D printed panels have better mechanical properties and better thermal resistance. The thickness of the board was 5 centimeters. We tried to reduce the thickness to 4 centimeters, but with 4 centimeters, you cannot keep the temperature below 100 degrees, 180 degrees for as long as 120 minutes. So you have a crossover at around 90 minutes. So it depends on the application, but this was a successful test. You can see here the curves for the 5 centimeter panel. A maximum temperature in this case 1200 degrees, and the temperature should have not become higher than 380 degrees. So this was again a successful successful test. The panel was not possible to print a panel that was occupying the entire volume. So this is based on 2 adjacent panels, but you can see that the panels can be also anchored to the other structures. So we were because of the porosity in the board, you can drill through the board without cracking. This is the 4 centimeter panel. In this case, we were aiming at 240 minutes, and you can see the crossover at around 180 minutes. So semi-successful test, but you can see that due to the refractory characteristics of the geopolymer, bear in mind that this geopolymer was not fired; it was just sprinted, and then it was directly exposed to the high temperature, and there are no significant cracks. The material remains integer. And this is the major advantage of geopolymers with respect to, for instance, cement. You can see here something that was done at the company. So for cable fire protection, service ducts, we can make large parts and parts with different shapes as well. This is a test for service duct, the fire resistant test, and the limit for the temperature was not crossed over. So this again is a successful test showing that we were able to achieve the desired results for this project. So sorry, I don't know why. Okay. So another project that we worked on. Okay. Sorry, I had many more slides about this project. I don't know what happened. Maybe I loaded the wrong file, but I can talk and then I can discuss the few slides that are here. So we have established that we can 3D print geopolymers using a wide range of raw materials. And we know that if we select the correct combination of materials, we can have a consolidated product that can withstand high temperature. And I'm sure you're familiar with the fact that in Italy, in Venice, we have glass manufacturers that are world famous. And you know that for blown glass or for any type of glass object that you want to shape, you use mold. And you can use either a metallic mold or you can use a wood mold. And a metallic mold works well for automated large volume fabrication. The molds are expensive, and it is not easy to find people these days that can make the mold. For artistic production, people use wood-based molds, and specifically wood coming from the pear tree. Don't ask me why, because I don't know that. And the reason, I assume it's related to the way the wood chars and can thermally insulate the rest of the mold without it burn out while you're using it. And there are sustainability issues with this type of approach because there are not many pear trees available these days for making molds with a certain size. So we had actually we have two regional projects for making molds for molten glass. And you can imagine that if you have molten glass and you have an inorganic mold, you need to make sure that there is no sticking of the glass to the mold. You need to make sure that the mold allows for blowing and rotating the part while after shaping. And we tested geopolymers for this application because of their high temperature resistance, and we were able to find formulations that would avoid, that would withstand the contact with glass, and to favor the detachment of the glass from the mold, because bear in mind that the mold is porous. We deposited a coating based on a geopolymer containing graphite that was able to anchor to the geopolymer mold and was able to be polished in order to achieve a good surface quality. Due to the limited resolution for this specific printer that we used, 5 millimeters voxel size, we have some precision issues, meaning that it is not easy to have a rotating part inside the mold because there are some defects still in the inner surface of the mold. But you can see that we can have luster surfaces, fully transparent glass. So if we further improve the quality of the mold, this is a suitable approach for making art objects. And I didn't mention this for metallic mold. You typically use it up to, I don't know, tens of thousands of times. For wooden mold, you typically use it between 100 and 200 times. And we reused the same mold up to 150 times without any issues in terms of cracking or degeneration of the surface. Of course, we need to, like in any molds, we need to reapply the coating after a few times. And we worked with an art school, and they came up with different shapes. And you can see that the advantage of additive manufacturing is that you can come up with any design. You can generate the mold rather quickly. It is very cheap, and it works well. In this case, the transparency is there. The surface texture was a design adds some design characteristics to the part. So we are still, and you can also you can see other parts that were created by artisans in Venice. We are working with specifically two companies. This is a modern company. This company was founded in 1289. So it's one of the, I would say, the oldest still existing company making glass. And Barovière is the one, Angelo Barovière is the one that invented crystal glass in 1450. So I demonstrated that with binder jetting of geopolymers, you can make parts for different applications. If you want to reduce the weight of the part, you can add lightweight aggregates, and you can find lightweight aggregates that are refractory. For instance, for the glass molds, now we are using perlite as a high temperature resistant porous material, cheap, that allows us to have lighter molds, but still performing well in contact with glass. So we are applying for another project with a region in order to be able to further improve the quality of the molds. And one of the things that we can do is, for instance, applying CNC using a robotic arm to polish the inside of the mold and obtain a better surface quality. We are interested also in large-scale elements for coastal protection. We were involved in a proposal for making artificial barrier reefs, and the project was not funded, but it was funded by the French government for the people that we applied with. So this is concludes the part on additive manufacturing of geopolymers. The reason why I wanted to talk about cellular ceramics is that they are a very important class of materials that bear a lot of contacts, interactions, and links to additively manufactured parts. And here I will be discussing mainly foams, but we have to think of foams as highly porous components, parts, and additive manufacturing of ceramics works very well for macroporous and parts. And that is why I think it is useful to learn a bit more about what porosity does to a material, to a component. And we can see that it adds a lot of functionalities. And of course, the difference between foaming and additive manufacturing is that foaming will give you a stochastic structure. So you generate a large volume of pores that have a range in sizes, and they are distributed typically homogeneously within the volume of the body. With additive manufacturing, you can create non-stochastic porosity. You can create porosity which is precisely designed with the size, shape, and amount that you desire. So this is an important difference, but all the other considerations that I will make can be applied to porous components made using additive manufacturing. And speaking of the use of ceramics made with made by additive manufacturing, you saw some samples yesterday. Some of them were simply showpieces, but the main applications at the moment for additive manufacturing of ceramics are dental crowns. I don't think this is still needs to be fully accepted by the customers, but instead of printing alumina, which is too white with respect to the color of the teeth, people are printing lithium disilicate, which is the typical glass ceramic material that you use for dental applications. So dental crowns is a very strong driver for the use of additive manufacturing for ceramics. Another very strong driver, and dental crowns are not non-porous, okay, but they are have a very complex shape. Another important driver for the use of additive manufacturing of ceramics is the fabrication of casting cores for turbine blades. I don't know if you're familiar with the technology, but turbine blades are made, of course, of metals. And in order to increase the temperature of use, they contain some channels that pass through a fluid that cools down the blade during the use. And these channels have to be arranged in space in very specific ways to provide the best cooling possibilities. And it's a very complex network of channels. And what people are doing is to 3D print these ceramic parts, which are the once you eliminate the ceramic, these become the pores. So you have the ceramic body that is extremely that has an extremely complex 3D structure. You pour the metal around it, and then you need to eliminate the ceramic part. And you do that by chemical attack, by dissolving it. So people use, for instance, silica as a material for these casting cores. For certain for certain materials, especially certain alloys, silica is not good enough, so people are shifting towards alumina. And you need to be able to remove the solid ceramic part. So the ceramic part needs to be partially porous, despite having the shape, and needs to be withstand thermal shock when the metal comes in, needs to have a certain strength to avoid breaking when the metal comes, needs to be at least partially dissolvable. So there is a lot of work going on in this field. The third potential, well, not potential, I mean, turbine blades are currently produced, at least in part, with this approach. A third field of application is electromagnetic wave absorption. So the advantage there is that you can work with the material in terms of the performance for reflection and absorption of the electromagnetic waves, but you can also work with the shape. And there are softwares that allow you to, based on the properties of the material, to come up with the optimized shape for absorbing the electromagnetic radiation in a wide range of wavelengths. And people that publish and work in this field they say it's for civil applications, and that's true. But when you're working with materials with high temperature capability, you understand that the applications are wider than civil applications. So these are some of the fields where additive manufacturing of ceramics is used, and most of these parts contain porosity. So here I will try to discuss first the structure of highly porous ceramics, and then I will discuss fabrication properties and applications. So this is quite an old presentation when I was still working on foams, ceramic foams, but it can be applied to additively manufactured ceramics. When you think of a structure of a porous material, you need to be able to identify the features of the material. If you want to predict some properties, you have to come up with some models that describe the pores within your material, and you need to be able to characterize the porosity in a quantitative way. And in terms of properties, of course, you can look at a wide range of properties, but for ceramic materials, people are mainly interested in mechanical, electrical, thermal, and permeability properties. I will mention the different ways of fabricating cellular ceramics. One of these methods is, of course, additive manufacturing, but I will not be discussing that. In terms of applications, here it's just a short list, but there is a lot of applications for highly porous ceramics. If you're interested in this field, there are some books available. So there is a wide range of cellular ceramics, and let me mention one thing. So cellular ceramic is a technical term that specifically is related to ceramic containing a large volume and porosity. And by large, typically people mention 70 volume percent as the threshold above which the material can be properly labeled as cellular. And the term cell was proposed by Richard by Hooke in the 17th century. So one of the early people working with the Royal Society in London, and he was studying cork, the structure of cork, using one of the first microscopes, and he observed the porous structure of cork, and he said that it reminded him of the cells in a monastery, and that is why he labeled the structure as cellular structure. So you can have foams that are specifically based on 3D arrays of polyhedral cells that are packed to fill space, with cell walls that are randomly oriented in space. You can have honeycombs where you have parallel prismatic cells. You can have 3D printed structures where you have, in that case, the example was given with struts, so filament-based structures. These days, with additive manufacturing, you can also make sheet-based structures, and these materials are called shellular materials rather than cellular materials. So based on shells, on thin sheets rather than filaments. You can make highly porous structures based on connective fibers. People have been using biotemplated structures for making ceramics, and there are also other possibilities for making highly porous structures. You can see here some examples of cellular materials in nature, and this means, so this is Robert Hooke's drawing of cork, 1665, and there is a reason why in nature you have a lot of porosity, because porosity adds an important functionalities to the material, as I will try to explain in a moment. Food also has a lot of pores. People say that in this way the companies are selling you air rather than a solid, but there are reasons, of course, beyond that, because it is related to the elastic modulus of the material. If you bite into something that is porous, the elastic modulus of a porous component is much lower than that of a solid material. There are issues related to the amount of geometric surface that you have available with a foam. So you have faster dissolution, more interaction with the papillary glands and things like that. So there are a lot of advantages in making advantages in making porous parts. When you talk about porous materials, one important feature is the pore size, or we can now use the term cell size because we're talking about cellular materials. And it should be noted that the UPAC definition of pore size is the one listed here. So you have micropores below 2 nanometers, mesopores between 2 and 50 nanometers, and macropores above that. And this was devised, this definition, for catalysts. And it does not make sense for macroporous components like a foam or a 3D printed structure. So you have to be aware of the fact that the terminology needs to be appropriate for the type of component you're discussing. Down here, you can see a wide range of possibilities for making foams, or highly porous ceramics. And here you can see a wide range of applications, from filtration to different types of filtration, diesel particulate filters, catalyst supports, enzyme immobilization, insulators, bioceramics, and so forth. So let's discuss first the structure of a cellular material. And you can have, this presentation was prepared before the advent of additive manufacturing, or at the beginning of the advent of additive manufacturing. So some of the comments are not really meaningful anymore, but you can have, for a cellular solid, honeycombs or foams, thinking of traditional ways of making these highly porous materials. And you can define a cell as a small compartment or enclosed empty space with solid edges. And of course, you can have faces, not just edges. And the faces, you also have faces, not just the edges of your enclosed empty space. And the faces can be solid or void. If you have a solid faces, then you have closed porosity. If you have void faces, then you have open porosity or interconnected porosity. And we are talking about cellular materials, and people have mentioned that there is a transition between the behavior of a solid with pores and the behavior of a cellular material. And this is at around, as I mentioned, 70 volume% of porosity. There are other types of low density solids that would classify as cellular solids, so beyond simply considering honeycombs and foams. So if you think of this enclosed space surrounded by edges and faces, which are properly termed cell walls. These are the features that you can identify in a cellular material. The edges are named called struts, and the faces are called cell walls. And again, you can have open or closed cell walls. On the left, you can see it's open. On the right is closed. The connectivity, so the number of struts reaching each vertex, is important for the properties. And bear in mind that when you make a foam, you cannot typically control the number of struts going into vertex. If you are, of course, using additive manufacturing, you can do that. There's an interesting point to make, that some properties depend mainly from the cellular structure and only weakly on the cell size. So this is interesting and leads to the fact that people tried to come up with an idealization of this cell shape, and you can have different 3D polyhedra possible, but only few of them are able to pack without being distorted in space to fill completely the volume. And people that have worked on this topic, they suggest that the most efficient way of packing voids of the same shape and size in space is based on this specific type of structure, tetrahedron, which I will show you in a moment. Bear in mind that real foam are often not based on identical units, but considering an idealized cell shape helps with modeling. So this is the tetrahedron, which is used as a model for the shape of a cell. And this was actually developed, it was actually conceived by Lord Kelvin in 1887. He was the first one to try to come up with a geometric component that would be able to fill the entire space in a regular way without being distorted. These days, there is a new structure that achieves, which is more efficient than the tetrahedron, which was discovered in 1994. You can see here two ceramic foams obtained using different materials. When you have a foam, ceramic foam, you can characterize the morphology of the foam using different parameters. You can evaluate the so-called strut size, so the diameter of the solid constituent of the edges of the material. You can compute, you can measure the cell size. And by the way, you can carry out, of course, you can do computed tomography, but that it's quite labor intensive. You can use optical or SEM images. And of course, if you have a cell and you have a cross section, you don't know in your sphere or in your structure where the fracture cut. So you get one size, but you do not know if it is the real diameter of the cell or not. And there are some stereological equations that allow you to convert the measurements from 2D to real 3D. You can find that in the literature. So you can quantify the cell size, and you can also quantify what is called the cell window size. And of course, you can have foams where you have fully closed cells, or you can have foams where you have a certain amount of porosity within a closed cell wall. So you need to be able to characterize all these features in your foam. And here you can see examples of different classes of cellular ceramics with different morphology. This is a 3D printed part. This is a space shuttle tile. This is connected holospheres. This is a biomimetic structure. The first one is a honeycomb. So when you do characterization of the foams, as I said, you can use computed tomography. This is actually a synchrotron radiation, because you can see the resolution is much higher than conventional, at least in those days, than conventional computed tomography. Now the resolution is about 3 microns for desktop tomography equipment, but with this synchrotron radiation, you can go below 1 micron in terms of resolution. So let me first mention the influence of processing on structure and properties and other characteristics. And you can, from the macro structure level point of view, you can obtain open, closed, anisotropic, graded cell structures. You have a certain cell size, you have a certain cell size distribution, you have a certain wall thickness, and of course, a certain amount of porosity. So you can control all these parameters. In terms of the microstructure, you can have hollow struts, so the solid component can be hollow. You can have oriented grains, you can have different types of surface finish in your cellular material. You can have residual porosity, and certainly you have a certain flow population that is important for controlling the properties in a ceramic material. Depending on the type of process, you can also have different types of compositional characteristics which affect different properties, including thermal properties, electrical resistivity, and so forth. And then, depending on the type of application, cost is also a driver for selecting the best procedure according to the specific features required in the final component. So I will go quickly through different ways for making foams, and then I will switch in the next lecture on discussing the properties. So one of the first ways of making a foam template was to use replication of the foam template. Other approaches include sacrificial templating or direct foaming of a liquid slurry or other methods. There is a nice review paper available that discuss all these different approaches for making different foams. So the replica method leads to the fabrication of what are called reticulated ceramics. And if you look at the patent, it was issued in 1961, but the interesting point is that it was issued to a guy working for GM, the car manufacturer, because the foams, ceramic foams, reticulated ceramic foams were used as catalyst support for cars. And with this technology is very simple. You have a slurry with your ceramic material. You have a polymeric sponge with open cells, and you simply immerse the polymeric foam into the suspension. Then you lift it, and the slurry has coated your polymeric foam, and then you sinter. Of course, you need to tailor the adhesion of the slurry to the polymeric template. You need to compress. The polymeric template is flexible because you need, once you dip it and extract it from the slurry, it is not the slurry not simply coats the edges of the polymeric foam, but it also fills, at least in part, the void. So you need to squeeze the foam to push out the unwanted trapped slurry. And then you need to fire to obtain your ceramic material. And there are a lot of parameters that you can work with in order to optimize the properties of the material when you make it. And typical characteristics of these materials are that they are fully open cell. They have a pore size between or cell size between 150 to 5 microns to 5 millimeters, high porosity. They have, for different reasons, weak mechanical properties, and they are very low cost. and they are made in large volumes. Actually, they are not, these are different types of materials that have been used for this approach. So actually, the main application is no longer with cars, because people use extruded honeycombs for that, but it is for multi-metal filtration. So you can see the polymeric foam, and in order to have such a nice open structure, what people do is that they make the foam and then they have a hydrogen-containing mixture that explodes and breaks all the cell windows, and you obtain a very nice interconnected porosity. After dipping and carrying out properly the process, you obtain the replica. That's why that's why this process is called a replica. The term for the material is reticulated ceramic. And if you don't expel completely the slurry, after sintering, you have certain amounts of cell walls, but you can still retain the permeability. So here, of course, the permeability is lower than there. One important feature of these materials, which explains why the mechanical properties are not very high, is that after you sinter the material, the polymeric material is completely decomposed, and you're left with a void within the strut. And the problem for the mechanical properties is not the fact that you have a void inside the strut, because that's not a problem. The problem is that you often have surface defects on the strut due to the fact, you can see here that the ceramic layer is very thin, and this is related to the shape of the polymeric template, which has very sharp edges. So people have tried to modify this in a way that I will show you later. But this explains why the foams have a very low strength. So this is the issues with this process, and that is why other people have developed other processes. Let me mention one important thing. So these cellular materials are very, very important from the technological point of view. Most of metallic components are produced by passing molten metal through a ceramic foam. And the reason is that the ceramic foam acts as a filler for unwanted oxides and slag components within the metal. And without ceramic foams, you will have a lot of problems. For instance, in the 1980s, one of the high-speed German trains, IC trains, broke down entering a station, and a lot of people died. And the reason was that the axis failed due to an oxide inclusion. So after that incident, after that accident, most of all the critical parts made with metal in Europe are processed through a cellular ceramic. The multi-metal goes through a cellular ceramic. Of course, these are single-use parts, need to be cheap, and that is why people don't make them using additive manufacturing for this specific application. On another point, the fact that you have a stochastic structure, a disordered structure, different cell sizes, it's actually favorable for this application, because you have a flow that is more conducive to allowing for the particles to be attracted and attached to the foams. So the foam acts better as a filter than a regular ceramic structure. So people have, for instance, tried to remove the void or to heal the struts by infiltrating the material, and you can infiltrate completely, or you can infiltrate just to smooth the corners of the inner features. And in this way, you can obtain better mechanical properties. Another way for making ceramic foams is to simply use sacrificial templates. In this case, you have some materials that volatilize during processing. You can use sawdust, you can use carbon black, you can use polymeric microbeads, starch, wax, and you can, in this way, generate a wide range of pore shapes. And you, depending on the volume fraction and nature of the material, you can obtain either closed or open cell structures. And in terms of the size of the materials that you use as templates, they can widely range in size. This is a list of the materials that have been used. You have, of course, issues in terms of gas evolution. So you need to be able to carefully control the burnout process, but people can do that. And this is a very cheap way of obtaining a large volume of porosity, even though the morphology of the pores is not always very good. You can also use non-fugitive inorganic phases. One interesting variation of this approach is to use ice as a template, as a sacrificial template. So people have been doing freeze drying and casting of a liquid-based slurry. So basically, what they have is a ceramic slurry, water-based, and they freeze it to obtain ice crystals, and then they sublimate the ice, leaving a porous structure behind. And this process can be industrialized quite nicely, and you can generate very interesting structures that are oriented. So it's tubular structures because of the way the ice crystals grow. And for instance, in Japan, there is a company making thermal insulating blocks based on silica using this approach. And they are very, very efficient, and it's a very cheap approach because you're not burning out anything. You're simply evaporating, sublimating ice. And there are different ways of controlling the shape of the ice crystals. And for instance, you can see that you can go from a lamellar structure to a structure where you have some bridging parts that lead to a more isotropic behavior for the material. Okay, I can skip. Here you can see some images of such structures, and by controlling the way you freeze, you can control not just the shape of the crystals, ice crystals, but also their dimension. And typically, the smaller, the higher the lower the temperature, the smaller the features that you can obtain. Another way of making foams is direct foaming, and this is typically carried out, for instance, for polymeric foams. So it's quite a straightforward approach, but you have to realize that making foams is not is simple, but you have problems with stabilization of the liquid foam. So because you have different processes that lead to the disappearance of the bubbles inside your liquid foam, and We are interested in liquid foams because after having the liquid foam based on a liquid, water for instance, and water, containing our ceramic particles and gas, then you can consolidate the liquid and obtain your solid foam that can be sintered. And there are easy ways of making a foam by mixing and embedding bubbles, or you can add volatile blowing agents. That can be liquid or solid. You can have in situ reactions that generate gas, or you can bubble and gas through a liquid. And the issues with foaming, with the stabilization of the liquid foam, is that you can have three phenomena that govern the making of the foam. You have, after you make the foam, you have drainage. So the liquid will drain through the cell edges until you reach an equilibrium state. You have coarsening. So you have the small bubbles that tend to disappear, and the large bubbles become larger and larger. And then you have the collapse of the foam due to the liquid film rupture. So people can use surfactants to decrease the surface tension of the system. So you stabilize the liquid gas interface. You can use the surfactants to control the cell size distribution, control the open and closed cell content, and also you can control the flow of the drainage of the liquid. So once you have made this liquid suspension embedding gas, so you made your slurry-based foam, you need to consolidate, you need to set the foam, and you can use gel casting. So you can add an organic monomer into the system that can polymerize, or people have been using all sorts of binders that are water soluble, for instance, starch or different proteins that consolidate the liquid. Or you can have, for instance, mix your ceramic powder with a polyurethane precursor, and you can foam directly the polyurethane precursor, forming a solid. Or you can use freezing, or in my case, you can use salt gel or pre-ceramic polymer precursors, and you have either gel or you can cross-link the pre-ceramic polymers. So there are some advantages with direct foaming. You can obtain both open and closed cells. You have a wide range of possible cell sizes. You have a much wider range in terms of the bulk densities, the amount of porosity that you have. The solid struts have a lower amount of defects with respect, certainly with the reticulated foams. And if you have a liquid foams that contains your ceramic particles, and then you can set it, then you have a large versatility in terms of shapes, because you can cast your liquid foam in any mold. And you can, playing with the parameters, you can obtain graded porosity or anisotropic cells. There are also issues. One is the difficulty in controlling precisely the foaming and the stabilization of the foam. You certainly have difficulties in obtaining a narrow distribution of cell sizes. Often, occasionally, but I would say often, you have both closed and open cells in the final material. And sometimes, since you're foaming, you're rising your liquid in one specific direction, often, or in some cases, you have anisotropy because the cells are not round, but they are stretched in one direction. I think I should stop here because there is time for questions. I would have simply continued discussing some features of these materials. You can see the structures here. One of the advantages I should mention of this approach, direct foaming, is that you have dense struts. So the strength of these materials tends to be higher. Okay, so let me stop here, and I'm open for questions concerning everything I've told you today, and of course, also in the past few days.
Sir, regarding the usage of slag, do you do any processing before using it? Or because generally slag contains a lot of deoxidizing agents, desulfurized agents, and so on. So are you targeting any particular phase of a slag, or you just take the slag and use it?
So at the moment, we're simply taking the slag and using it. The only processing that we do is that we grind it because in order to make it more reactive, we need a higher geometric surface area.
Generally, it contains multi-phases. So
yes,
you are not segregating the phases.
No, we're not. I mean, for the applications we are looking at, specifically large-scale additive manufacturing of inorganic components, we don't mind the type of phases that are present in the slag because we're just interested in using a dissolving part of the slag to make the geopolymer network. But if you think of high temperature applications and you're using that type of material, then you're correct. One should also consider what kind of phases could develop with firing or high temperature applications. Yeah.
My question is related to cellular ceramics. How the cellular structures is different from PPMO structure? How the cellular ceramic structure differs from PPMO structure, like diode structure, lattice structure.
Oh, lattice structure. Okay. Well, I would say that the difference is that in a lattice structure, the cell shape is very different. And in terms of the entire volume of a cellular component or a strut-based component, typically in a strut-based component, you have a regular non-stochastic structure. So that's another major difference. And one of the things I didn't mention, so ceramic foams are kind of easy to produce. They have a lot of advantages. They are not expensive, and they could serve. And people have demonstrated already in the 90s that you can use them effectively as catalyst support for a wide range of applications. And the advantage of using a monolithic component, which is the same advantage that you would have if you're using a 3D printing part, is that you have a much lower pressure drop. And in a foam, you get also some turbulent flow inside the part because you have channels in all sides, from all sides. And this helps with the reactions. The reason why this has not been implemented more in industry is related to the fact that it is very difficult to have homogeneous behavior for these materials because you can, when you purchase, for instance, the polyurethane and you measure the permeability of different blocks of polyurethane, you find different results. So I was discussing this with a professor from KIT, Karlsruhe Institute of Technology, and she's a chemical engineer. She was the first one to publish about one of the first ones to publish about the advantages of using a ceramic foam with respect to, for instance, pellets-based catalysts. And she said that she stopped working on that topic because of the unreliability of the performance. Of course, now with additive manufacturing, you have a strong advantage.
That is why I asked this question. And one more thing, like even we make foam structure, for some space application, as you mentioned, the space shuttle. That space shuttle needs some kind of foam structure with random orientation of force, actually, interconnected force. So there is always some trade-off between strength and the conductivity. Like we need low thermal conductivity as well as higher strength, actually. Higher strength. Higher strength. Strength.
Strength. Sorry, apologize. Yeah,
So
sure.
there is a trade-off
Yeah.
between in terms of strength as well as conductivity. So in what basis we can fine tune both the property, like
So there's software that allows you to do topological optimization based on FEM analysis. And one of them is called NTOP. It was used to be called N-topology. Now it's simply called NTOP, NTOP. And it is a software that allows you to do topological optimization. So you can optimize strength, thermal conductivity at the same time. One issue with that type of approach, which is where the field is going, is that you're missing the link between the object that you have designed and the fabrication possibilities, because you can come up with the best shape in the world, but if you cannot actually print it, then you are in trouble. So with, for instance, DLP, one could say, well, I can print, in theory, any shape. Yes, but then the size is very small. Typically, yesterday we saw a large slab. This is actually, there are not many companies that are able to produce such large components. So the link between topologically optimized structure and manufacturing still needs to be improved.
How do we do the strength then for highly porous structures?
So good point. People have found that sheet-based structures have a better mechanical behavior at the same total porosity. So for strut-based structures, you have differences depending on the shape of the repeating unit. So if you have octahedral cells, if you have other types of structures, you have either a bending-based behavior or stretching-based behavior for the solid elements in your cell. And for ceramics, stretching-based structures are more performant at the same amount of porosity. If you shift from filament structures, struts, to sheets, then you further improve the mechanical property. So TPMS structures are now one of the best kind of structures that you can generate, optimizing at the same time strength and porosity.
Sir, what are the different ways to remove the air bubbles trapped?
Different
Air
ways
bubbles. If you are making a paste or the
Mhm.
precursor, so there is a high possibility that air gets trapped.
Yes.
So what are the different ways? People are using some deformers to remove. So what is your opinion on using deformers?
So, I mean, in this, for this process, I want to have bubbles. For instance, when I make pastes for directing writing, where the viscosity is very high, there are people that use defoaming agents, or you can apply vacuum. We have, for instance, and for making highly viscous pastes, there are some specific mixers that work best. So we have two sets of mixers that can mix a large quantity of powders inside the liquid to make a highly viscous paste. And then we have vacuum defoaming before we use the paste. Then you still have the problem that you need to insert the paste into the syringe. It takes a little bit of practice to avoid adding other porosity. But there are ways in which you can obtain bubble-free slurries. Yeah.
Suppose we have two matrices, aluminum and aluminum oxide. So one is purely metal-based extrusion we wanted to do, and the other one ceramic-based extrusion. So what do you suggest? No, which one will be easy? For example, if you are doing extrusion method, so it is easy to extrude aluminum or aluminum oxide.
So I don't have I don't have any experience with extrusion of metals. A colleague of mine is working using our printers to print metals. I would say that from the point of view of rheology, probably metals are a little bit easier to extrude because the particle size is larger. With metals, I think you have more problems with sintering because you have to avoid the presence of anything that can react with the metal. So with a ceramic material, it's a little bit more straightforward. But from the rheological point of view, I would say that, and also it is easier to find ceramic particles than fine metal particles. They are pyrophoric and they oxidize easily. So I prefer ceramic particles.